Finding vertical asymptotes. Quite a problem. But we can always start with an example of a vertical asymptote. So here you can see the very famous example of f of x equal to 1 over x. We have a clear vertical asymptote on the y-axis. And if we recall what an asymptote is, it is a point or a value which the function always approaches but never reaches. In this case, it's a point, and it's the point x is equal to 0. And the reason why it never reaches it is mainly because it's not defined there. So that is an example of a vertical asymptote. And in fact, most vertical asymptotes adopt this behavior, or they assume this nature or this property which the 1 over x function has, the inverse function has. And that property is the asymptote or the double asymptote. And so we can actually find different asymptotes by looking at the singularities. So clearly, at x is equal to 0, there's a singularity. But can you try to pause the video and think about which singularities can we find in this expression? Can you list all of them down? And what happens if we take a limit as we approach these points, these possible asymptotes? So think about that. For me, I don't need to think about it because I have my singularity check right here. So it's not difficult to see that if we are here, plugging in 0 in 1 over x is a problem, and plugging in x is equal to 2 in this fraction is of course also a problem. Usually, I mean, just by looking at it without doing further inspection. But the thing is, after you do the singularity check, well, this is a possible vertical asymptote, but it doesn't have to be a vertical asymptote. Well, how do we know? Is a good question. And the answer to that is we need to compute the limit. So in the first one, your problem is x is equal to 0. In the second one, your problem is x is equal to 2. These are possible vertical asymptotes, but this is not for sure yet. Here is how we check. We said x tends to 0, so x tends to 0. We also said x tends to 2, so we let x tend to 2 of y. So we take the limit of y as we approach these points of singularities. So now I just need to do some work. I will start by calling this L1. I'll call this, maybe I'll call it L0 because it's for x is equal to 0, and I'll call this L2 because it's for x is equal to 2. Then I will take a look at L2. Just make a small split here. So L2 is this. I can write it. I can distribute the limit on both summands because the limit of the sum is the sum of the limit. And you'll see in a moment why this is useful. Just one moment. Yeah, we're almost there. So this is now two limits. The first limit why wouldn't we plug in? What is stopping us from doing so? Nothing. This is a continuous function. This is also a continuous function. So the limit is just sine 1 over 2 times 2 squared. So it's 4. This is, of course, the sine of half, and then you multiply by 4. And then we have, so it is more precise to say that this will be the answer for the limit itself, not just for the green part, so to say. And then the second limit, is there really anything we can do with it? Well, there's something I can do. I can choose u to be equal to x minus 2. Then if x tends to 2, then u tends to 0. I will not write this down. But on a very simple level, it is easy to see that this will be true. Because if you're approaching 2 here, you're approaching 0 here. And this is the very famous 1 over x function, and we are approaching 0. So this must be a vertical asymptote. So x is equal to 2 is a vertical asymptote. Now, next we look at L1, and I think you've already noticed that, oh sorry, it's L0. And I think you've noticed that I've left it for now, because it may or may not be more interesting. You know, it's very important to build up your arguments. So just like with here, this is simple. 1 over x minus 2 is a function which is continuous at every single point except that x is equal to 2. I'm talking about this function. So I can just plug in. So this will be 1 over 0 minus 2, which I think is minus 2. And so it's minus half. This is the second limit. But what about the first limit? First limit is actually quite something. I'll call it, let's say I call it L. So this means that L0 or L naught will be equal to L minus half. So this is L. And for some reason this seems to be similar to many things we've done before. I don't know if you see this as well. But with usually we had sine of something, and we had x, and then we had a limit that goes to 0. This is usually very interesting for us, and we can link it in fact with the following. So just from practicing limits and doing lots of stuff, we know that this is somewhat similar to that. It's not quite that form, but you get this feeling. And let's assume that you don't get this feeling. You don't have to get this feeling. The best way to proceed, the very best way and the recommended way to proceed is that when you see there is a function inside of a function, and you see there's a function inside of a function, and you cannot, for example, bring the 1 over x outside, then you should make a substitution, a u sub. So this is a function, this is the function sine of x, but you compose it with Yeah, okay, that's quite okay. I literally just wrote the same thing. So you're composing sine of x with 1 over x, and that's what's happening. So we did do u sub because we were confused, we don't know what to do. And then hopefully everything will work out. First question is, if x tends to 0, then if x tends to 0, then where does u tend to? U tends to plus or minus infinity, right? Because you take the limit, it's obvious you're going to 0. We literally just showed ourselves the graph. You go to 0, so you go up and down. Okay, next we have sine of u, because u is equal to 1 over x. And if u is equal to 1 over x, then x is equal to 1 over u. And so this is 1 over u squared, right? I hope that is clear, just by the u sub. And then I'll just borrow one of the two u's, and I'll write the other one here. So this is the moment where you actually get to use... that is another thing. That is a completely different thing. We don't use the hint. In fact, I don't think this is useful for this case. But if you think about it for a moment, it's a good direction to go to. So it is very often in mathematics that you don't know exactly where you will land, but you know how to proceed, and that is very important. So we were proceeding with the thought in mind that we will land onto something of this form. Sine u over u. But we did not. Nevertheless, this is partial progress and it should be celebrated. And it can be celebrated, in fact, because we know what the value for this limit will be. It will be 0. And the reason for this is that sine of u is a bounded function. Let me write this down. So no matter what the value of u is, the sine function is always has a range between -1 and 1. As for the denominator, it's u squared, and with u squared, the denominator is really exploding because you're plugging in plus or minus infinity. And if you have something that's, it is at least -1 and at most +1, and you're dividing this thing by a very big number, then you'll get a very small number. And that is why this limit is equal to 0. Another way you could reason about this without having to write this whole bit is you can look at this limit. The limit is going to 0, and you can take it as a fact, more or less, that the x squared function grows faster than the sine function. So if it grows faster, then it will beat it to 0. It will be at 0 before this can reach its singularity. So this goes to 0 before it goes to, let's say, infinity, for example. So this should give us infinity, and this should give us 0. But if you get into this speed race, then you will find out that this indeed wins the race. X squared is the winner. And if this limit is 0, then our L0 is actually equal to, if it's equal to L minus half, and L is equal to 0, as we've just shown here, then this whole limit will equal to minus half. So for us, this means that our point is not a vertical asymptote. And I will show you now a graph of the function so that you can believe me. There it is. So at x is equal to 2, I don't know if you see this clearly. So we have the same behavior, almost the same behavior that we see with 1 over x happening at 2. So no matter how close we get, we can always zoom in and we will find space. So it will never touch the line 2. It will only get close to it. Which is, yeah, it's sad. Some things are just not meant to be. But that is not the case for x is equal to 0, because if we go to the point x is equal to 0, which is right here, it's there, then it is corresponding to the point minus 0.5. So I'm glad that this is actually the case. We've computed the value of the function at 0, and we got minus 0.5. So the function indeed is defined at that point, and there is no vertical asymptote. This is it.